Well, good evening, students. This lecture is supposed to start at 7:30, but I've waited for some minutes to allow some of us to join. Time does not wait for anybody, and so I think the best option for us to do is to begin, to start. And, what I have to do is to share my screen. Move ahead. Okay, good evening once more. My name is Professor G.A. Abu. I still remain your facilitator, your guide in the 303 spatial relativity. Last week, we were behind by just a week, but we started last week. And what formed our objective was, our topic was just an introduction. We were able to go through how this course is going to go. That is the structure of the course, how we are going to go through through the materials. And we ended it up with the natural frame of reference, which we thought is a very vital topic for us to begin. Today, just as I promised last week, that it was not going to be easy for us to talk about the natural frame of reference and as well as that of a Galilean transformation. So today we are going to focus our attention to Galilean transformation. Our learning objectives are going to be that you should be able, at the end of this lecture, you should be able to write down Galilean transformation equations and its inverse. It will demonstrate the invariance of equations of Newtonian mechanics under Galilean transformation. As well, we are going to perform some simple calculations involving Galilean transformation of physical equations. If time permits, we talk about the Michelson-Morley experiment. That's the way we are going to go today. We discussed all this last time. So, including Newton's equations. Now, this is the Galilean transformation equation, the Galilean transformation, which we are about to begin. We talked about the natural frame of reference last time, and we also asked a question on the situation whereby we have two persons at different frames of reference. One in a moving car, one stationary on the ground, and both of them are made to measure the length of a rod, either in the moving frame or in the stationary frame. And we ask ourselves that if both of them have measured, are taking their readings of that of a rod, we ask that question, say who is moving. So we are past that aspect, but here we want to relate that to Galilean transformation. That is a situation like that, where you have two observers. The two observers, if you look carefully, you see that an observer is in in S frame. That is, we assume that this frame is not moving. And another observer, O prime, is in S prime frame. That is prime frame. And if you look at the beauty of this is that you see that they are in Cartesian coordinates. The Cartesian coordinates X, Y, and Z axis. That is the first frame, the S frame, that is the unprimed frame, and the prime frame is also designated by X prime, Y prime, Z prime. Now the situation here is when the two frames coincides, that means when you see this O prime being at the position of O, S prime being at the position of S, that means they coincide. At this position, the time t is equal to 0. Now, just like we said, the person who is on the ground and someone who is in motion in a car that is moving, you see that the S prime frame has now left the S frame. The observer is at a certain distance from here to here now, because that frame has moved this space of time. And that space, of course, we know that that space, if you want to calculate the space, is velocity times time, which is this dt. Velocity times time. That's if you now use, you now say displacement is equal to, velocity is equal to displacement over time. Velocity. Let me put it, velocity. Okay, it's not writing notes, pen. Let's say that velocity is equal to displacement d over time. So that means this distance from here to here is dt. That means if you take this distance, and if you take d, the subject of the formula, d is equal to vt. That's where you now have that vt. This vt here. This vt you have here. Now, that means that this O prime has been displaced by a distance d. And the distance to this particular point, if you look at a point, a particle at this point here, you see that that is the point of an object both of them are looking at. Both the person who is at O frame, both, that's the person, the observer at S prime, and observer at S prime, and observer at unprimed S. They are looking at this object to measure. Now, an object is in the frame that is moving. So you see that the distance between the objects to which they are to measure from the observer, O prime, is X prime. That is because the measurement is along X axis. There's no movement along Y and Z axis. The motion is along X axis. So we now look at, okay, I say, okay, this is the force acting on that object, assuming there is a force acting on this object. But what they are to measure is an object that is here at the point P. Now, we look at this and say, okay, what is this X prime? what is this x prime? Remember that from here, let me use the cursor, a pointer. From here to here is the distance x, the observer in the S frame has to measure. But remember that this frame has moved a distance of vt, and that the distance of the observer from the object to be measured is s prime. So that means that this x here is equal to x prime plus vt. And so when you now you make x prime the subject of the formula, you now see that x prime is equal to x minus vt. Because there is no movement along the y-axis, you see that y prime is equal to y, z prime is equal to z, and t is equal to t prime. From the course material, we observe that this is equation 1.2. And so this is now what we have as Galilean transformation equation. That is equation relating the measurement measured by an observer O in S frame and that of an observer O prime in S prime frame. Then these equations, because they are equations, these equations are what we now use to relate the measurements both of them have made. But remember, we said that relativity deals with space and time. So from here, we see that frame of reference which are in translational motion at constant velocity, which is this O prime, relative to each other are called inertial frames of reference. Even this one is at least an inertial frame of reference. That is the unprimed frame, because here there is no motion. But the S prime is moving at constant velocity. And once it's at constant velocity, that means acceleration is zero. Remember that acceleration A is equal to velocity over time, v dt. Now, if velocity is constant, is not changing, that means derivative of this is zero and dv dt will be equal to zero. That means acceleration is equal to zero. So any object or any system or any frame that is acceleration is equal to zero is taken to be an inertial frame of reference. Or that any motion or frame of reference whose motion is at a constant velocity is taken to be an inertial frame of reference. That is what you have observed here. So let's move. You can see that you can see what these equations represent. And you see that we just got them from here. So that is Galilean transformation equations. Now, what about its inverse? Let's see the next slide. Okay, the next slide is the invariance is not written here, but I think it is what I will now do. So the invariance is it's just a change of the signs of these equations here. So the invariance of Galilean transformation will then become x. Let's put that together. It will become x. We make x the subject of the formula. X equal to x prime plus vt. X prime from plus vt. Y equal to y prime. Z equal to z prime. and t prime equal, t equal to t prime. And this set of equations is what we refer to as the inverse of Galilean transformation. Remember, it's one of those things we say that is one of our learning objectives. At the end of it, we'll be able to now know that, we'll be able to write them down. So, any question from here? So we'll move ahead. Now we have seen the Galilean transformation. What we want to test now is to see if this Newton's second law is invariant to the Galilean transformation. Whether it has the same form as in, whether it is as in prime frame and unprimed frame, whether the equations are going to remain the same. So that will now take us to recall the xy components of the force acting on the particle in S-ray. Remember, last time we talked about those F components from, if, can I even see the point of the writing point? Okay, let me use one. And so remember that Newton's equation is F equal to ma, or v squared v over t squared, squared. That is Newton's second law of motion. Now, in the Newton's law of motion, we need to remember that F is a vector and velocity is a vector. So F equal to, the vector F is equal to I F of x plus J F of y plus K F of z. And with that, you look at the components here. For velocity, v is equal to I v of x plus j v of y plus k v of z. Now, when we look at this, you now see, okay, that let us take component by component of the force. In the unprimed frame, that is S frame, let us write that equation as Newton's second law of motion in the unprimed frame. Now, this F of x will be md squared x over dt squared. Because here you have velocity, you have the velocity here. That will be Vx. That will be Vx. Yes, that will be Vx. So, but here, we are talking about, okay, I think I made that mistake first. Let's look at, let's erase this. That will be dv. That will be dv dt. Dv dt. We now erase this. Dv dt. Now, the velocity is at, because this space is not this space is not so. So V equal to IVX plus JVY plus KVZ. Now, the component of the force along x-axis. That means, but we know that our velocity V is a vector as well. So what we need to do, how do we put in this? Because the velocity is also, because I want to put it in a situation whereby let's velocity velocity V is equal to the R over dt. And we know that R is equal to I x plus j y plus k z. So if you need to have velocity, I mean acceleration, which is the vdt, you see that it is going to be y's derivative of x here. So that means that our m here retains itself. The component of the force along x-axis will be m d squared x over dt squared. F of y, that is component of the force along y-axis, is equal to m d squared y over dt squared. And that of f of z is m d squared z over dt squared. This was taken as our equation 1 last week's lecture. So this is the component of the force. This is the component of the force in the unprimed frame, which is the Newton's second law of motion. Now, in the frame that is primed, for us to get this component of the force, we now see that we take that Galilean transformation equation and differentiate it once. Remember that what we had was x minus x prime minus x prime. Let me this. It's making it to be. Got it. X prime is equal to x minus bt. That is the first equation. So we differentiate this x prime with respect to dt prime in the prime frame. And that is going to be derivative of x over dt, which is this second expression here, minus, if you differentiate this with respect to t, you now see that what is left is v. Again, we differentiate it again, that is twice. The second one, the second time will be the x squared prime over the t squared, and that is equal to the squared x over the t squared. Why we left this the t prime? Remember that from our equation 1.2, that t is equal to t prime. And so dt is equal to dt prime. So the dt prime here will be replaced by dt here. And we also have dt here. So you can look at this. So if you look at this, you now see that if you now do the same thing along a y-axis, you still get the same expression. That is, in other words, here you have the squared y prime over the t prime squared equal to the squared y over the t squared. The same thing similarly to that of z. Now, having obtained this, you can see that we have just differentiated Galilean transformation twice. And then we look at the components, we multiply that derivative by m. So that we can now have f of x, the component of the force on the x prime axis will be mass times the squared x prime over the t squared. Along y-axis is you multiply by m, you still have m. Along z-axis, you have that, and that is what we have as our equation 1.3. When you compare this equation to equation 1.2, you'll find out that they have the same form. That's nothing changed. Remember, equation 1.2 is f of x equal to m d squared x all over dt, squared. F of y is the same thing, m d squared y prime, or not y prime, the dy over dt squared. F of z is going to be m d squared z all over dt squared. So if you look at it, you see, you look at this and this, you see they are the same. Look at this and this, they are the same. Look at this and this, they are the same. So in other words, because they are the same, they have the same form. Nothing changed. So by virtue of this, we now say that the equations are invariant under Galilean transformation. It does not change any form. That's the Newton's second law does not change. It does not change under Galilean transformation. So that is what we now obtain. So you're able to now see that when we have Newton's second law of motion, we test it, we observe that this set of equations, that's Newton's second law of motion, does not change any form. It remains the same. They are the same nature, either in the prime frame or on the prime frame. At least, once again, you see that one of our objectives have been achieved. So, for us to see how this is being applied in some of the problems that we have, this is what we are going to do. We now take some examples because one of the objectives is that we have to take some work examples and see how those things are being applied to our problems. So in this case here we have, I don't know why this thing is hiding. Using my mouse. Okay, it is not hiding, but it is tiny. It's tiny. Just because it's tiny, so I look at it and so here, what example number 1? It's a man in a boat moving at constant speed of 60 kilometers per hour relative to the shore, throws an object forward in the direction with a speed of 30 kilometers per hour. What is the speed of the object as measured by an observer at rest at the shore? What you need to do is you look at the equations again. See, a man in a boat. This man in a boat is likened to be the moving frame of reference, which is S prime frame. In a boat at constant speed that means the speed of that boat in the S prime frame is 60 kilometers per hour. Relative to, with respect to somebody who is at the shore, who is on the ground that is not moving. And this man in the boat throws an object forward. That is, the boat is moving ahead of him and he throws an object with a speed of 30 kilometers per hour. So, but the person who is at the shore is still observing him. But what he has to measure is to measure the velocity of the object in the moving frame. So what he now says is that the person now says is, what is the speed of the object as measured by an observer at rest? So the observer at rest, which is at the shore, what is he going to measure? That is the person who is on the S frame. the frame that is not primed. So what is going to be is that in order to solve our problem, we say let VB be the velocity of the boat and VS be the velocity of the boat. I mean the velocity of the speed or velocity of the object thrown. Now, the velocity of the observer V in terms of VB and VS, that is the velocity of the observer in the shore, will then be the addition of velocity of the boat because the boat is already moving and somebody who is in the boat throws a ball that moves also at a certain speed of 30 kilometers per hour. In other words, the person who is on the ground is going to measure the speed at which the boat is moving plus the speed at which the ball thrown is moving. In other words, you now have that the velocity is going to be VB plus VS. And that will give us 60 plus 30, and that becomes 90 kilometers per hour. So somebody who is on the shore, he sees the ball to be moving at 90 kilometers per hour. But to the person who is in the boat sees the ball moving at a velocity of 30 kilometers per hour. You can see how both measurements have been related. That's one good example of our application of this Galilean transformation. A second example is also shown here, and that is a passenger in a train moving at 35 kilometers per hour looks out and sees a man standing on the platform of the station at t equal to t prime equal to 0. You note that. What are you going to note? This man standing on the platform of the moving train becomes the prime frame. So 20 minutes at that time, when he was looking outside, the two coordinates, that is the one that is stationary and the one he's standing on, which is now in motion, both of them coincide, and their time remains the same at t equal to 0, at initial time t equal to 0. But what happens now is 20 seconds after, the man on the platform, that is the man on the moving train, determines that a bird flying in the same direction as the train is 800 meters away. He has made his own measurements. 800 meters away. So, what is the average speed of the bird as determined by the observer or by the passenger? Now, we look at it. Let's look at the coordinates. The coordinates of the bird as assigned by the man on the platform is x, y, z, t. That is the frame he is. And x is 800 meters, y is 0 because the object is not moving along y, neither is it moving along z. It's only moving along 800, along the x-axis. And his timing is 20 seconds, that is later. The distance of the bird as determined by the passenger. You will write down that passenger who is inside the moving train becomes x prime equal to x minus vt equal to 800 minus 35 times 20 minutes. It's 20 minutes, 20 seconds, but I have already converted it into meter. So you now have 800 minus 35 times 20. Of course, that will give you 700. So 800 minus 700 will give you 100 meters. So the person who is in the prime frame will have his own measurement is 100 meters. The coordinates of the bird as determined by the passenger are s prime, y prime, z prime, t prime. which is now 100 meters, 0, 0, because there's no vertical, there's no movement along Y, along Z axis, 20 seconds. What I should have written here is either to remove this or either to remove it or put it in seconds. Now, first, the average speed of the bed as determined by the passenger is what? That would be 100 divided by 20, because we know that velocity is equal to this displacement over time. So that means 100 over 20 seconds, and that is 5 meters per second. And again, what is the question? The question says we should determine the average speed of the bed. So we should determine the average speed of the bed. That's what the question is saying. And so because of that, yeah, and so because of that, we have determined the average speed of the bed, which is 5 meters per second. Now, this is supposed to be the activity in the other frame. That is the other question where we have the natural frame of reference. That's the first lecture we had. It would have been that. And with this problem, let's even solve another problem. Let's just, instead of just ending up here, because we have about 15 minutes left. I don't know if we'll be able to now treat the last point of it, Michelson-Morley experiment. It will not be easy for us to go through it. So in order to cover the time, what we need to do is to pick up another problem and then see how we can do that. So let me unshare and share again and go to the whiteboards. And this is whiteboard. So the question, the problem we need to solve now, we want to see one more application of this Galilean transformation. The question here is saying that, I don't know what, let me just put something this way. If I should type it, a passenger or, okay, no. A swimmer can swim. Let me type it. Let me see if I should type it fast. A swimmer can swim with a speed c in the still water of a lake in a stream in which the speed of the current is v. The swimmer can also swim with a speed c relative to the water in the stream. Suppose the swimmer swims up to a distance L, and then returns downstream to the starting point. Find time taken to make the round trip and compare it. Time taken to swim across the stream, the distance L and return. Don't know, sorry. Don't know. A swimmer can swim with, let me bit. The speed c in the still water of a lake in a stream in which the speed of the current is v. The swimmer can also swim with a speed c relative to the water in the stream. Suppose the swimmer swims upstream a distance L and then returns downstream to the starting point. Find the time taken to make the round trip and compare it with the time taken to swim across the stream, the distance L, and return. Now, that is the question. Now, what we need to do now is, what we need to do now is to solve this problem, this kind of problem. And so, for us to solve the problem, what we need to do is, first of all, we can I even see the, that's what's the problem I just have. So the solution, let's sketch what the problem is like. This is the stream bank. This is the stream bank, and you see that this is the velocity. This swimmer's velocity, VA, and this is the velocity with which the stream is moving. And here becomes C, which is swim with a speed C in the sea water. If it is sea water, this is what it's going to look like. So this is the bank of the river. Now, if you look at this problem, let's draw it, the bank. This is stream bank. You see that if the person is moving this way, that is along with the stream, the velocity is going to be c plus v. But if the swimmer is moving against the water, it's going to be c minus v. While the stream is flowing here, the velocity v. Now, we now let the motion of the swimmer as seen by an observer at rest with respect to the banks of the stream is what we have just drawn now. So we now see, let the round trip to cross the river be TA. To cross the river be TA. And let the round trip time to cross the river, the TA. That's the time to cross the river, is TA. And the round trip time downstream and upstream, the TB. So here, what we are going to do is to say that we begin with the swim across the river. That is, if this one, let's say this is across VA. So we begin with the swimming across the river. And we notice that to swim across the river is perpendicular to the banks. That means here, just as you have seen, it's perpendicular to the banks. This is the one side of the river, just as we have drawn it here. So it's perpendicular to the river is this, and swimming across directly is that. But there's no way you can do that because there's no way, that's in every case. But if the water is still, but if the water is pushing, it has its own speed. You see that there's no way this person is going to cross, because if the river is flowing this way, the force of the river will be pushing the person by the side, and that is exactly this path that we follow until now crosses. So the swimmer must aim at an angle, which is this angle. He must aim at an angle upstream so that the upstream component of this velocity compensates the stream speed downstream. So he must aim at an angle. And that angle is this, because this one would be, the stream force will be pushing this one by the side. So what we need to do is that we now have, using Pythagoras theorem, we now see that because this will be here, and this will be by vectorial addition. So by Pythagoras theorem, you see that VA, which is this, VA squared is equal to C squared minus B squared. You know, Pythagoras theorem says VA squared plus V squared is equal to C squared. But now we are looking at this velocity. That's why we now say V squared. So V squared equal to C squared minus V squared. Where VA, we know, is the velocity of the swimmer. It's the velocity of the swimmer. What is coming up here? It's the velocity of the swimmer perpendicular to the banks of the stream, perpendicular to this. That is this axis. So if we want to get VA, we make VA the subject, because this is squared. We make VA the subject of the formula, and what we are going to have will be VA. I don't know, it's going to delay me. VA is equal to C into 1 minus V squared all over C squared raised to power. I don't know if you're asking questions on that. That means what we are doing here is we say, if you look at this equation here, we take C squared minus V squared and say that divide both sides by C squared. If you divide both sides by C squared, what you need to do, you have, or you have C squared outside 1 minus V squared over C squared. When you now take the square root of this, you now have that this is V squared is equal to C squared. So if you now take the square root of that, what we are going to have V, implying that V is equal to VA is equal to C square root of 1 minus V squared over C squared. And we know that this square root sign is the same thing as this 1 over 2. So that's what we are going to have. So what about the time? The time to cross the stream along the straight direction across will then become, will then be the time to cross, which we have labeled as a TA, or capital A, is equal to L, which is the distance across VA. Remember that this is not a different thing. Velocity is equal to displacement over time. That's what the idea that was used here. So now that we have used, of course, this is our TA, not even small letter t. So we now substitute our value. We now see that L, our value for VA, L over C, L over C into 1 minus V squared over C squared raised to power minus 1 over 2. I know some people may be asking a question on this because what we got was C into 1 minus V squared over C squared raised to power half. But because this one is inverted now, so everything becomes inverted. So with this, we now make TA. We now have to with this expression here. This journey is twice the total time taken. The total time taken will be 2 times TA. That is why you have 2L over C into 1 minus V squared over C squared raised to power minus so the journey is 2 times. So we now consider the swim or the swimmer, the swimming parallel to the banks of the stream. We've got the time. So the velocity downstream is C plus V, because if you are moving along towards the direction of the flow of river, you'll be moving quicker. That is the velocity, the 2 velocities will add together. But if you are moving against, that means you'll be struggling. So the other one moving against, if you're moving downstream along the same direction, if you're moving against the downstream, upstream, it is a C minus V. So the time for the round trip, simply, the time for the round trip, which we now say is TD, will then become L over C plus V plus L over C minus V, because that is together. So what we need to do is to get the LCM of this, get the LCM of that. This and this will be C squared. The LCM, if you take the LCM, will be C squared minus V, minus V squared. Let me break it down. Here we have, okay, it's writing. Let me clean up this. So you have C. What is Okay. So you have, let me use C plus V times C minus V. You have C times C is C squared. C times V is minus CV. And this times this is plus CV, VC, or the same thing as CV. And plus minus here is minus V times V is V squared. That is where this and this is the addition, this subtraction. So they go there and we have C squared minus V squared. So this plus C plus V, dividing this, you now have L as a common factor. That will be into C plus V, C minus V. Both of them are C minus V. And this other one here will be the same L into, okay, no, not the same L. This will be, this will be plus, because of this plus sign here. Because you know that always where the problem, where I cover my problem here. Then I want to see it. So we now have a plus L into C plus V. So when we do that, we now see we multiply out this and this. We open up, not even multiply out, we open up. This is LC. This LC minus LV, this is LC plus LV. And what we are going to have will be 2LC. 2LC. Let's open up. Let me we have LC minus LV plus LC plus LV. You can see that this and this negative here, positive here cancels, and what we have is 2LC. That's divided by C squared minus V squared. My fan is off. See what I was running away from. So, but here you now see that this is for TB. So what our problem is going to be will be by you now have bring out what we are going to do is to bring out 2L, that will be 2L over C, because if you divide both sides by C, that is here numerator by C, you divide this here by C, divide this one by C, what we are going to have will be 2L over C. That is here. Okay, let me just see. Multiply up by C squared, multiply down by, multiply numerator by C, multiply denominator by C. We have this. So what we are going to have will be 2L over C, which is this one, into 1 minus C squared over V squared. But for us to have our related expression, this is going to be, this one is an inverse. If you take it as an inverse, then you get it. But if you don't want to, just leave it as it is. So the question now is comparing TA. What is this? Is our TB. This is our TB. So if you compare TA, this is our TA. So we want to look at this to do the same thing. So we now see that our T is 2L over C into 1 minus B squared over C squared. Instead of B to raise to power 1 here, it's going to be raised to power minus 1 because it's an index now. So if you look at this, our TB and our TA. So what are you going to see now? What are we going to see now? You are going to see that the two round 3 times are different. They are not the same. This is raised to power half. That is, this one is raised to power minus half. This is raised to power minus 1. So the time, of course, they are not going to do the same thing. It will take you longer time if you are going upstream. But if you are going downstream, it's going to be shorter. So you can see it that it comes out to play here. That the 2 times are not going to be. In fact, definitely in practice, there's no way it can be, the 2 times can be the same. The 2 times will be different because 1 is moving downstream. If you are moving downstream, you are moving in the same direction of the stream. You see that the velocity of the stream adds to your own velocity and you move faster. And that means it takes you shorter time to move downstream. And if you are moving upstream, that means it takes you longer time because you are moving against the stream direction. So you are encountering some forces to overcome the forces of the direction of the push of the water. So moving upstream becomes harder. And so the time is longer. So from here, we can end up this. Then that of a similar experiment, and we put it as a instructional video. You watch it maybe before the next lesson or the next lecture. You should be able to tell me what and what you observe. But in this case, this one, we are. I'm waiting for any question that may come from you concerning this. Just put down your questions. When we meet, we will now talk about that. So for me here, it's good night.